Hi everyone, today we're going to be learning about the derivative. And the derivative is one of the big three in calculus: limits, derivatives, and integrals. So this is a really important concept. And the derivative has to do with the slope. So first I want to review a little bit about what you already know about the term slope. When we talk about slope, you're used to talking about it in terms of the slope of a line. And so we would have 2 points. And in order to find the slope, and we'd use the letter M to indicate it, we'd look at the change in the y over the change in the x. And that would tell us the slant of the line. Shapes and objects in the real world aren't all just straight lines. So what we have to do is we have to think of a way to come up with the slope of a curved line. Here's a curve, and I want to know what the slope is. What's the average slope? Well, I can go back to my original definition of slope, where I look at the change in the y over the change in the x. So I have 2 points here. I have a point at x, f of x. And I'm going to indicate on this that this distance between here and here is h. So if this is x and this distance is h, then this is x plus h. So this x value is x plus h, and it's the same curve function. And in order to get my output value, I would input that into my function. So this is the notation that I have for the curve using the value of h. So it says find the slope using the given points. All right, so we're going to just do what we're used to doing. We're going to take the change in y and put it over the change in x. The change in y would be f of x plus h minus f of x. And the change in x would be x plus h minus x. And now we want to simplify what we can. Well, there's nothing we can simplify in the numerator, so we're going to just rewrite that. And in the denominator, we have x plus h minus x, so we're just left with h in the denominator. So this right now then is giving me the average slope of this curve from this first point to the second point, with h being the distance in between. And there's a term for this. It's called the difference quotient. Now, here's where it gets really interesting. If you can imagine that that value of h is going to get smaller and smaller, and we keep shrinking that value of h. If we keep shrinking it and we keep getting this distance closer and closer together, we'll end up with slope at a tangent point on this curve. So if you shrink h, in other words, you take the limit of that function as h approaches 0, as h gets close to nothing, you will get the slope of the tangent line at a point. Right? So again, I'm going to say that again because it's really important. As we look at the limit as h approaches 0, we're getting the slope of the tangent line at any point on this curve. So we could get this tangent line, or this tangent line, or this tangent line, and each of those lines has its own unique value for slope. So that is what we call the derivative. The derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. So the derivative is the slope of the tangent line at a point on the graph. So just to be really clear, let me give you another quick example. Here's a curve. And this curve has many different slopes. So we have a slope here, and here, and here, and they're all different. So the derivative is the limit of the difference quotient. And the derivative, instead of being the average rate of change, is going to be our instantaneous rate of change. So we know precisely on the curve exactly what the instantaneous rate of change is at any point on that curve. And that's a little bit better than looking at just the difference quotient by itself and getting just an average. So here's some visual examples of a derivative. If we're looking at this graph right here, the derivative exists everywhere on this graph. So we've got a slope here, we've got the slope of a tangent line here, slope of a tangent line here. These are all tangent lines and all different values for slope of all those different tangent lines. There are times when the derivative does not exist, and there are three different cases. The first case is a corner. If you're looking at the graph here, the derivative exists here, we have a slope there. The derivative exists here, we have a slope there. But the derivative does not exist at a corner. I mean, that's because you wouldn't really know exactly where to draw the tangent line. You could really draw it in infinite number of places. So on this graph, at x equals 0, the derivative does not exist. It exists over here and it exists over here, but at a corner, precisely at the corner, a derivative does not exist. Another case where a derivative does not exist on a graph is when we have a tangent line. So right here on this graph, it's going vertical. It's a tangent line right there. And as you know, when we're talking about the slope of a vertical line, it doesn't exist. The slope of a horizontal line is 0, but the slope of a vertical line is undefined. So at x equals 0, precisely on this graph, the derivative does not exist. Now the derivative exists elsewhere on the graph. We have a derivative here, we have a derivative here, we have a derivative here, right? But it doesn't exist precisely at 0. Now the third scenario where a derivative would not exist is when we have something called discontinuity. And we're going to do a whole lesson on discontinuity, so we're just going to briefly touch on it here. But a function is said to have discontinuity if it is not continuous at a point on the graph. So at x equals 0, the derivative does not exist for all of the below types of discontinuities. So at x equals 0, we can't draw a derivative because we have a jump discontinuity. We have a break in the graph right at x equals 0. Now we have derivatives before x equals 0 and derivatives after x equals 0, but not right at x equals 0. So the first one is jump discontinuity. The next one is point discontinuity. So we have this open circle. So at x equals 0, there's nowhere to draw the tangent line. We can't draw a line against nothing. There's nothing at x equals 0. Now, that's a little bit different than looking at the limit at x equals 0. We do have a limit here, but we don't have a derivative at x equals 0. So that's point discontinuity. And then the last case is infinite discontinuity, where we have a vertical asymptote and we have a discontinuity with that break because of that vertical asymptote. And this graph at x equals 0, the derivative does not exist. All right, so derivative will not exist at a corner, at a tangent line, or at any of these three discontinuities. All right, so let's recap that a little bit and look at some notation. This is what we defined on the first page, and this is what we call the limit definition of a derivative. For shorthand, we could write f prime of x, or we could write dy dx. These all mean the same thing, and they're all asking you to do the same thing. They're all asking you to find the derivative. When you evaluate using the limit definition of a derivative, we say that we are differentiating from first principle. So another way of saying it. Another word for slope is gradient. You're going to see that a lot on anything generated by IB. gradient is another word for slope. So when we say use first principles to find the gradient function, we mean find the derivative. Again, just to recap that, these all mean the same things. Find the derivative, find the derivative, find the derivative. Differentiate using first principles, it just means find the derivative. Okay, so use first principles to find the gradient function f prime of x equals x squared. So we're going to use the limit definition, and we're going to write it down first. Now, when we use the limit definition, we need to know what is f of x plus h. Well, we know f of x is equal to x squared. I'm just going to write that over here. F of x, we're given, is equal to x squared. But I need to know what's f of x plus h. So I'm going to replace x with x plus h. So f of x plus h is just x plus h squared. You replace x with x plus h. All right, so let's go back to our limit definition. We know that for this particular function, f of x plus h is x plus h squared. And f of x is x squared. Let me just circle those. Right, so I replaced f of x plus h with x plus h squared. I replaced f of x with how we defined our function x squared, and that's all going to go over h. Now we're just going to go ahead and find the limit. Now you can see that if I take the value for h as h approaches 0 and I put it into this function, I'm going to get 0 in the denominator. So I have to do a little bit more work before I can use any kind of substitution. So I'm going to expand x plus h squared. Then I'm going to subtract x squared, put it all over h, and continue to simplify. Now, I've expanded my x plus h squared, that's this guy here, and I have tacked on my minus x squared at the end. So I'm going to be able to cancel the x squared parts of the numerator. And now let me rewrite with those canceled. Now it looks like I can pull an h out of the numerator, and that's going to really help me out. And now you see what can happen. I can cancel out the h's. And finally, I'm at a point where I can use substitution. I can put 0 into this function, and when I do that, I get 2x. So 2x is the derivative. And again, what did we say is the derivative? Well, the derivative is the equation we can use to find the slope of the tangent line at any point. So we can say f prime of x is equal to 2x. And that's our solution. So let's take a look at the graph on the calculator and see what does this really mean. So I put in my function into y equals x squared, and I'm going to do zoom 6. And so if you're looking at this, and we have a parabola here, and we want to know the slope anywhere on here, I know that my equation to find the slope at any point on this curve is 2x. It's the derivative. So let's say I needed to know what's the slope of this curve at -2. Well, if I put -2 into my derivative, 2x, 2 times -2 is -4, I know that the slope at -2 is -4. If I put a value of 0 into my derivative, 2 times 0 is 0, I know that my slope at x equals 0 is a horizontal line at 0. It's a slope of 0 at the point 0. Let's say I put x equals 2 into my derivative. At the value of x equals 2, well, 2 times 2 is 4, I'm going to have a slope of a tangent line at the value of 4. So hopefully you're starting to see a little clearer what do we mean by the derivative. It's the equation to find the slope of the tangent line at any point on the curve. Now, At this point, if you are a little confused, I would highly suggest to pause the video, rewind, and watch it from the start again. Pretending like, you can just move forward and you're not quite clear, you're really going to do yourself a disservice. Take the few minutes and just go back and rewatch the beginning of this video. Now we're going to do the same process again. Find from first principles the gradient function of f of x, where f of x equals x cubed. So the first thing we're going to do is we're going to write out the limit definition of a derivative. And what I like to do is right under f of x, I like to add f of x plus h, just as a note to myself. And remember, what you're going to do is you're going to replace x in the original function with x plus h. So f of x plus h is equal to x plus h cubed. All right, so our limit as h approaches 0 is equal to f of x plus h, which is x plus h cubed, minus f of x, which is x cubed, all over h. Now what we need to do next is expand x plus h cubed. Now you can do x plus h cubed the traditional old-fashioned way, x plus h times x plus h times x plus h, and use the distributive property, but I'm going to do it the shorthand way because I remember the binomial theorem. And the binomial theorem says that I would look at the fourth row of Pascal's triangle, or I could use combinations. And the fourth row of Pascal's triangle I know is 1, 3, 3, 1. I have x and h. And I'm going to start at 3 for x and work my way down to 0. I'm going to start at 0 for h and work my way up to 3. And then I'm going to clean that up. So that's the expanded x plus h cubed. Now, if you didn't remember that and you think I'm crazy right now, I'll do the old-fashioned way here. We're going to just write it all out and use the distributive property. So I'll do this part first. So we're going to get x squared plus 2xh plus h squared. And that's going to all be times x plus h. And I'll multiply it by each term. And I'll take h and I'll multiply it by each term. And I'm going to line it up under the like terms. Combine like terms. And you could do it that way as well. Either way, I got the right answer here. I got the right expansion. But I think my first way is the best way. So let's fill it in now. So I have my expanded x plus h cubed, and then I have minus x cubed all over h. And now you can see that we're able to cancel the x cubed terms. And we can pull an h out of the numerator, and now we're able to cancel the h. And now we can use substitution. We can substitute the value of h is equal to 0 into 3x squared plus 3xh plus h squared, and we're going to get the final answer here, which is 3x squared. So the derivative of our function is equal to 3x squared. Okay, this is the last one. If you really want a challenge, try to do it on your own. I would say at least give it a shot, and when you're ready, come back and take a look at my work. All right, so we're going to find the derivative. We're going to find the equation to find the slope of the tangent line for the function 1 over x. So the first thing we're going to do is we're going to write the limit definition of a derivative. Over to the side here, I'm just going to make a note to myself that f of x plus h equals 1 over x plus h. I replace x with x plus h, and so then I get 1 over x plus h. Okay, so now at this point, We'd love to be able to use substitution, but we can't because we'd have a 0 in the denominator. So now what we need to do is your favorite thing of all time. We need to find a common denominator for the numerator and rewrite the numerator. So my common denominator is going to be x plus h times x. And that's going to be all over h. All right, so I'm going to be rewriting this with the common denominator of x plus h times x. So all you really have to do here is compare this to the new denominator. And what is extra? Well, x is extra, so that's what goes up top. And again, we have our new denominator, and you're comparing this to the new denominator. What's extra? X plus h. All right, let's clean that up. It's a little messy. So in the numerator of the fraction at the top, we have x minus x. You have to make sure you distribute that negative all over x plus h times x, and that's all over h. Let's continue to clean that up. So x minus x is 0, and we're left with negative h all over x plus h times x all over h. We're almost there. We have a fraction in a numerator and really divided by another fraction, h over 1. When we do that, to clean that up, we can multiply by the reciprocal of the denominator. Phew, almost there. We're going to cancel the h's. And now we can use substitution. We're going to replace h with 0, and we're left with negative 1 over, basically we have x times x, or negative 1 over x squared. So our derivative, the equation to find the slope of the tangent line at any place on this curve, is equal to negative 1 over x squared. And if you made it this far and you aren't crying, I'm very proud of you. All right, guys, lots of practice on this. No worries. Have a great day.